Interested in interactions among the matter particles, the fermions, and there are here 4 types of interactions. The electromagnetic interaction, the force carrier is the photon. The coupling goes like E, the coupling constant, times Q, the charge, and the leptons that take part in it are the charged leptons only, because the neutrinos are neutral, and it was vector-like, parity, charge conjugation, and CP, conserving, and diagonal and universal. Then there were the neutral current weak interaction carried by the Z boson. The coupling has various ways of writing it. This is the one that many use. G over cosine theta weak times T3 minus sinus squared theta weak times the charge. And the Z couples to both the charged leptons and to the neutrinos. And the couplings are chiral, different to left and right, parity and charge conjugation violating, CP conserving, diagonal, and universal. The charge current weak interactions are those carried by the W plus and W minus vector bosons. The coupling is G over square root of 2, and it couples to a pair of antineutrino and charged leptons, or neutrino and positively charged lepton. And these couplings, again, it couples only to depth-ended fields, so it's parity and charge conjugation violating, but CP, their product, conserving, and it's diagonal and it's universal. And the Yukawa couplings, I did not go over that, but the Higgs couples via the Yukawa coupling to the charged leptons. And in the slides that I skipped for the interactions of the Higgs boson, one could see that all interaction to fermions are proportional to the fermion masses, and its couplings to pair of bosons are proportional to the mass squared of the bosons to which it couples. And so in this sense, we should perhaps not be surprised that it doesn't couple to the neutrinos, because they are massless. And if it's proportional to the mass, then the neutrinos do not couple to the Higgs boson. So this is what we found about the interactions. A few comments. I think I mentioned already in the past that the weak interactions, it's really a misnomer. It's a misleading because they are not weak. G, the coupling, is larger than the coupling constant of the electromagnetic interaction, E. This is about 0.6 something, this is about 0.3 something. What they are is short range. So while the QED interactions are mediated by a massless photon, and therefore the range is infinite, goes like 1 over r squared, the weak interactions are mediated by massive vector bosons, be it the W or the Z, and therefore it exponentially falls at a distance which is 1 over mw or 1 over mz, and is negligible in the distances larger than that. And this is what makes them so difficult for experiments. This is why you have to build huge experiments with the hope that they will interact and stop them. I did not go over the vector boson self-interactions. There is, for example, coupling photon to W plus W minus. The Z couples to W plus W minus. The point I want to make here is that also these interactions depend just on these 2 gauge coupling constants, G and G prime. Equivalently, we can change variables from G and G prime to E and sinus squared theta, but this huge richness of interactions are all described by just 2 parameters, so the first 3 of these. And the Yukawa has 3 additional Yukawa couplings, or equivalently the masses of the charged leptons. So this is about the interactions. Next thing is accidental symmetries and counting of parameters and identifying the parameters. So, we said that always the accidental symmetries, if there are accidental symmetries, are a subgroup of the global symmetry of the kinetic terms. For the fermions in the kinetic terms have a very large symmetry. You can do any rotation in the space of the three left-handed lepton doublets, L1, L2, L3, or any unitary transformation among the three lepton singlets, the E-rights, and each of these will keep the kinetic terms as they are. But the Yukawa terms break this symmetry. Still, there is left a symmetry U1 cubed, which is electron number, mu number, and tau number. And charges not entirely trivial. Both the electron and the electron neutrino have the same charge under U1e, are neutral under the U1 mu and U1 tau. Both the muon and its neutrino partners have the same charge under U1 mu and are neutral under U1e and U1 tau. And both the tau and the tau neutrino have the same charge under U1 tau and are neutral under the other two U1 factors. And this has consequences. And here are some examples of the consequences. The decay of the muon, this is the main decay mode of the muon. The muon goes to electron, anti-electron neutrino, and muon neutrino. So we see that this conserves muon number. It's 1 in the beginning and 1 at the final states. And it preserves electron number. It's 0 in the beginning, and it's 0 at the end because E minus has charge +1 and Ni bar has charge -1. Sorry, under U1e. So it allows that, but it forbids processes like mu minus to E minus gamma. Okay, that's the only remaining symmetry of the imposed symmetry. U1 electromagnetism allows that, but the accidental symmetry forbids it because it breaks both U1 mu and U1e. Such a mu decay to electron, positron, electron, same thing. And similarly for various tau decays. So these things are searched for. And for example, the upper bound, there are dedicated experiments looking for mu to E gamma. And the upper bound on the branching ratio of mu to E gamma is now at the level of 10 to the -14, which means that an experiment has to produce some 10 to the 15 muons at least, and be sure that there are no 1 or 2 background events in this. It's a very challenging thing. The expertise for this is in Switzerland, in the Paul Scherrer Institute, and each time they break their own record and bring it down. Such things are also searched in the LHC. None of these has been seen, and so nature so far is consistent with these accidental symmetries. Well, not exactly, I'll go back to it. But for charged lepton decays, it is consistent with this. Also in scattering, for example, E plus E minus going to mu plus mu minus is allowed because it carries charge under neither of these three symmetries. But E plus mu minus to E minus mu plus is forbidden because it violates U1e and U1 mu by 2 units each. And I included here only examples with the E and the mu, but similar things apply to the tau lepton. And again, no such process has been observed so far. There is an additional ingredient in that. That's the accidental symmetry. A subgroup of that is the sum. So electron number is the number of electrons minus the number of positrons. Electrons and electron neutrinos minus the number of their antiparticles. Muon number is the number of muons and muon neutrinos minus the number of their antiparticles. And similar for U1 tau. A subgroup of that is what's sometimes called the diagonal subgroup, electron number plus mu number plus tau number, which is the total lepton number. The number of negatively charged leptons and neutrinos minus the number of positively charged anti-leptons and anti-neutrinos. And this is a subgroup of that. And so total lepton number is conserved in the leptonic standard model as an accidental symmetry. But the neutrinos all have charge under U1L. Each of them has charge +1 under this lepton number. They are leptons, either Ni or Ni mu or Ni tau. And the fact, we said that the fact that they are neutral under U1 electromagnetism, naively we would have expected them to get masses because it's not forbidden by the remaining symmetry. However, since they are charged under accidental symmetry, it explains why the Majorana mass terms are forbidden for the neutrinos, and actually it's forbidden not just in the leading order, the tree level, but to all orders in perturbation theory. We'll come back to it later. But the accidental symmetries are a consequence of doing just the renormalizable terms. And indeed, already in dimension 5, the lowest dimension of non-renormalizable terms, there is a term that breaks all of these symmetries. So you can make a dimension 5 term, 2 lepton doublets and 2 Higgs fields. So let's see, all of these are doublets of SU2, and of 4 doublets you can make a singlet. And the hypercharge is -1/2, +1/2, +1/2, so they sum up to 0. And actually, this set of 9 possible terms, because I and J, well, it's symmetric, so it's actually only 6 possible terms. So 6 independent terms. So all of these are allowed, and it breaks in general, since it can be like LE, LU, or etc. It breaks the entire symmetry at dimension 5. When we come later to neutrino masses, which violate this prediction, the most reasonable interpretation of neutrino masses is that we've seen for the first time the signal of a non-renormalizable term compared to the standard model, not just the leptonic standard model, but also compared to the standard model Lagrangian. And I'll say a few words about that. On one hand side, we say, perhaps we shouldn't be surprised that the first signal of beyond standard model physics that we see is from dimension 5, from the lowest dimension non-normalizable. The effects of higher terms will be further suppressed. This is suppressed by, for the masses, by v squared over lambda, while dimension 6 will come with 1 over lambda squared. On the other hand, it should worry us a little because the neutrino masses imply that if these y's are of order 1, then this scale lambda is 10 to the 15 GeV to account for neutrino masses. And then if all non-normalizable terms are suppressed by such a high scale, it will be very difficult to see the signal of even higher order terms. But it could be that lepton number is broken at that scale and other things happen already at lower scale. Yeah, I'll skip several of these. It's a little bit technical. So I was asked in one of the previous lectures, we started there with a mass matrix which was 2 by 2 and complex and ended by just 2 diagonal terms and real, which so instead of 8 complex parameters or 8 parameters that appear in a generic 2 by 2 complex matrix, which is how it was written originally, we learned that only 2 combinations of these, the 2 real diagonal terms, are physical. And so there is a question, how do we know how many physical parameters there are? So the previous 3 transparencies that I just skipped explain that. So it's a little bit technical. If you are interested, look into these previous slides. Here I just say the consequence. So the leptonic standard model have 7 parameters, 7 physical parameters, and we can write them in various, we can make various choices as to how to present these 7. So these are the original 7, the ones that appeared in our original Lagrangian, the 2 gauge couplings coming from the covariant derivative, 2 parameters related to the scalar potential, the vacuum expectation value V, and the quartic coupling lambda, and 3 Yukawa couplings, YE, Y mu, Y tau. All of these are real, so that's the signal that the model doesn't violate CP. So that's one way to present them as originally presented. Another, just to show that there are many ways in which you can fix and many ways in which you can test the model. So you can also use 6-dimensional observable parameters and 1 dimensionless. So the masses of the W, the Z, the Higgs, the electron, the muon, the tau, and alpha, the QED coupling constant, these and these can be exchanged. You measure one, the other set is fixed, and vice versa. And finally, I guess what should be called now the Magnificent 7, the one that are best measured, the set of the best measured parameters of the leptonic standard model. Some already appear, some not. Alpha, G Fermi, which is roughly 1 over V squared times the number, the mass of the Z, the mass of the Higgs boson, and the masses of the 3 charged leptons. And again, I think it's very impressive that the measurement of the Higgs boson already made its way to the best measured parameter of the model. Yeah, so I will not go into the low energy test. The low energy test is meant to say that even before our accelerators could directly produce W bosons and Z bosons, okay, I'll just present, there were low energy tests at energies well below the W and the Z that could tell us, already test this model, tell us a lot about its parameter, allow us to predict what are the masses and many other things, and among them a set of all kinds of neutrino and charged lepton scatterings which have been measured. And for example, this ratio of 2 cross-section is the fact that it should be 3 is a consequence of the fact that the mediator is a vector boson. So that's a proof that the mediator of these processes is a vector boson. And this ratio is yet another way to extract the value of sinus squared theta weak, and again, consistent with all previous ones. So let me summarize the leptonic standard model in this way. We started from a definition, okay? That's this, 4 lines, I'll put it on 3, but okay, I'm generous and put it on 4 lines. The imposed symmetry, the fermionic content, the scalar content, and the requirement that there is spontaneous breaking. This led us to this slide, the Lagrangian of the leptonic standard model. That's the most general, renormalizable Lagrangian made out of the scalar and fermion fields that we defined as part of this model, including also vector boson fields, gauge boson fields that were forced upon us by imposing a local symmetry with terms that are allowed and terms that are forbidden. So, for example, no masses, no fermion mass terms, but we could have Yukawa couplings, no trilinear scalar couplings in the original Lagrangian, but quadratic and quartic, etc. So all of this is coming from the definition. And based on this, we could explore the phenomenology. And we got this table. So we had to identify the mass eigenstates, which is quite different from the degrees of freedom that we introduced in the beginning. Thank you. Right, we had a W triplet and a B singlet for the 4 degrees of freedom, or for the 4 gauge bosons. And here we have the massive W minus and the Z, the photons, which are different from the original degrees of freedom. Just one scalar, real scalar, remains out of the 4 that were included in the beginning. The other 3 degrees of freedom do not disappear. They went into the longitudinal component of these 3 vector bosons. And in the mass basis, we identify 3 charge -1 leptons and 3 neutral neutrinos. And for each of these, there is a well-defined property or charge or representation under the exact symmetry. So under the Poincare symmetry of the Lorentz, the spin is well-defined. So each of these has a well-defined spin. Under U1 electromagnetism, which is the symmetry that is there in the end, then we have this list of charges. Most of these states do not have a well-defined SU2 cross U1 symmetry, charges, because they can mix such states only under the unbroken symmetry. So that's what we do here. And we could extract which are massive, which are massless, and the dependence of the parameters of the model. So that was the first step at phenomenology. We understood what are the elementary particles. And again, the elementary particles, what we mean by this, are the mass eigenstates of well-defined transformation properties under Lorentz and the exact symmetry of the model. These are things that can be measured in experiment. Then we went on and investigated the interactions and got this list of interactions among the matter particles. 4 types of interactions: electromagnetic, Z-mediated, W-mediated, and Higgs-mediated. We got the way that the mediator couples to pairs of leptons, and which leptons experience each of these 4 types. And we identified the accidental symmetry of the model and the number of parameters, 7, and presented various ways of what are these 7 independent parameters. And that's the investigation of this model, starting from the definition, going through the Lagrangian, and ending up with the spectrum, the interactions, the accidental symmetries, and the number identity of the parameters that are independent. And that's actually things that we've done also in previous examples, but this is the closest to nature. Actually, all of these are parameters of the standard model. All of the accidental symmetries here are the accidental symmetries of the standard model. The spectrum of the leptons is the same, and of the vector bosons is the same. There are additional vector gauge bosons, we'll see that, but the list here is still also there. And the interactions among the leptons will remain exactly the same as we presented here in the standard model. So this is a large part of the standard model, but also a large part of how we will work our way through the standard model. So now that I start the standard model, quite a few things will repeat. So I will repeat them, sometimes in a shorter way, because I think it's not so bad to hear it twice, I hope. But this is really very close to many things in the standard model. What is missing are quarks' strong interactions. And we'll see that the W interactions with the quarks introduces additional new phenomena that do not exist in the leptonic standard model, something called mixing. CP, which is a good symmetry of the leptonic standard model, will not be a good symmetry of the standard model, and we will understand why and what's the difference. So that's the leptonic standard model, and we can move on to the main topic, or I don't know, the main topic, the title of this series of lectures, the standard model. So, the red bar goes one more down. I think we are crossing by that half of this. I'm not sure that we'll finish the standard model now or tomorrow morning, but we finish it early enough that I can also do some of these. So let me take this opportunity and tell you things that what I think. So I think I'll skip 3 of these: flavor physics, QCD at the IR, and flavor changing neutral currents. It's a big sacrifice because my own field, in recent years at least, is mainly flavor physics and flavor changing neutral currents, but it's fine because all the others are also. So first, after we finish with the standard model, we'll talk in general why we are convinced that there is beyond the standard model and in what ways we think about this. What's the logic of the various searches for such physics? And then we'll discuss Higgs decays because that's a way to search for new physics. But also it's the main program now at the LHC, the Atlas and CMS. So we would like where the experimentalists are to understand what they are trying to achieve. Neutrinos, because it's the only solid evidence based on terrestrial experiments that shows that the standard model is incomplete. And if time allows, also cosmological tests so that we know a little bit more about dark matter and why neutrinos are not T-dark matter, and the baryon asymmetry and why the standard model cannot explain the baryon asymmetry. So that's the program for today, tomorrow, and 2 hours instead of 3 on Friday. So this is very similar. It makes my life easier. I can take the slides from the LSM and kind of sometimes just repeat them. Perhaps erase the word leptonic here and erase the letter L here, and I think all the rest is similar. So I said there is a method here. We will define the standard model. From that definition, we'll get the most general renormalizable Lagrangian made out of the standard model fields and obeying the symmetry that we impose. After writing the Lagrangian, we will obtain the spectrum, the interactions among the fermions, we will identify the accidental symmetries, we will count parameters and try to identify what they are. So that's the program. And here is the definition. So I'll repeat it again and again because I want to share this sense of, the fact that the standard model describes 5 types of interaction and accounts for thousands or tens of thousands data points successfully, and its definition is 4 lines, is for me, I'm impressed. So the symmetry that we impose is a local SU3 cross SU2 cross U1. The subindex here C says color. L here stands for left, Y here stands for hypercharge. So this part we already saw for the leptons, and this now is new compared to the leptonic standard model. There are 3 fermion generations. Generation means a set of representations, let's say a fermionic representation of this group, a set of different representations. So we'll see, we write here there are 5 different representations, but there are 3 copies of each. And these copies we call generations. So 3 generations, each consisting of 5 different representations. And I give them names. Q left, it's a triplet of SU3 color, it's a doublet of SU2 left, and it carries hypercharge plus 1/6. And the L and the R stands for left-handed or right-handed. Let me perhaps make a comment which maybe is not obvious. If I have a U right I have also a bar or overline U right, the antiparticle of the U right. and it's the conjugate representation. So if U right is a right-handed field, triplet of SU3 color, singlet of SU2 left, and carries hypercharge plus 2/3, the model necessarily include the antiparticle in the sense of CP conjugate of this, which is, you can write overline on the U right, or U bar left. It's a left-handed field, the anti of this, CP conjugate, so right turns to left, which is 3 bar. 3 bar is a difference, also of a representation of dimension 3, but different from 3. It's the complex conjugate of this, under SU3 color, also a singlet under SU2 left, with hypercharge minus 2/3. And since I guess that many of you have seen the Dirac equation which required antiparticles, which predicted, in a sense, the existence of antiparticles, this is what the antiparticles it predicted are the CP conjugate. So I personally don't like to use the word antiparticle for the charge conjugate particle. This is not what the Dirac equation predicted. It predicted the CP conjugate, which has the opposite chirality, has the same charges as the charge conjugate. But the existence of the particle does not imply necessarily the existence of a C conjugate particle. It does imply necessarily the existence of a CP conjugate. Okay? And indeed, all of these particles here, in nature there are also their CP conjugate, but not their C conjugate. Okay? There is no Q left, which is 3 bar 2 minus a sixth. No such representation in nature. So the model breaks C, and it breaks it already here in the definition of the model. And it breaks P. There is no Q right with these quantum numbers. Break C and P separately, but in the spectrum, all the CP conjugates are there as necessary. In the Dirac equation from quantum field theory. Okay, and I'm only here, so the third representation, I call it D right. So right-handed chirality, triplet of SU3 color, singlet of SU2 left, hypercharge minus a third, and these two we know from the leptonic standard model. Left-handed lepton doublet, which is a singlet of SU3 color, hypercharge minus a half, and a right-handed field E right, singlet of SU3 cross SU2, and carries hypercharge minus 1. So under SU3 color, we have in the fermions either triplets or singlets. The triplets we called quarks. The singlet we called leptons. So that's the names of these two. And those CP conjugate will be antiquarks and antileptons. There is a single scalar multiplet, phi, which is a singlet of this additional SU3 color, and similar to the leptonic standard model, a doublet of SU2 with hypercharge plus a half. And there is a spontaneous symmetry breaking of the SU3 cross SU2 cross U1. The SU3 is not broken spontaneously. The SU2 cross U1, as in the leptonic standard model, is broken to the U1 electromagnetism subgroup. So we employ the same scalar to do it. The fact that the scalar that we employ is a singlet of SU3 color already tells you, and this is the only scalar in the theory, that SU3 color will not be broken here spontaneously. If we wanted to break SU3 color, we should have included a scalar field that transforms under SU3. If it's a singlet, cannot break this symmetry. So that's the definition of the model. The group, fermionic content, scalar content, and the pattern of spontaneous symmetry breaking. Many things here repeat, as I said, verbally, things that were written in the leptonic standard model, but it's better to do it twice than not to do it. So we are after the most general renormalizable Lagrangian made of the fermion fields, this set of 15, 3 times 5, so the index I here goes from 1 to 3, and a single scalar field phi, with the transformation properties under the symmetry defined in the previous page, which is subject to the SU3 cos SU2 cos U1 gauge symmetry. This symmetry, as a first step, before we write the Lagrangian, we should do the following. The symmetry has 12 generators. The 8 generators of SU3, the 3 generators of SU2, and the single generators of the U1. Okay, for SUn, the number of generators is always n squared minus 1. So 8 generators for SU3 and 3 generators for SU2. This is the SU3 commutational relation of, this is the algebra of SU3, the commutational relation of the generators. F, A, B, C are the structure constant of SU3, known numbers. This is the algebra of SU2, the commutational relations of the generators of SU2, epsilon ABC, known numbers of the antisymmetric tensor. Generators of different factors in the product group commute with each other because they are from different groups. So we have 12 generators. It means that to have local invariance, we imposed a local symmetry. We have to introduce 12 gauge boson, if you want, degrees of freedom, an octet for the SU3 color, which is a singlet under SU2 cos U1, a triplet for the SU2 local symmetry, which is a singlet under the SU3 color times U1y, and something which is neutral under all, a singlet of SU3, a singlet of SU2, carries no hypercharge for the compensating or fixing the non-invariance due to the local U1 transformations. So the model necessarily, once we impose this local symmetry, have these 3 if you want. It's 12 degrees of freedom, but it's really 3 things. The octet of SU3, the triplet of SU2, and the singlet of everything. We continue with the automatic procedure, the things that are forced on us, that are part of the procedure. We define field strengths for the gauge bosons related to non-abelian symmetries. There is this extra term that depends on the structure constant and has 2 gauge fields. Similarly for the W, as was in the leptonic standard model, this additional term, structure constant and 2 W fields, and the simple one for the B gauge field. There are here 3 gauge couplings because there are 3 factors in the local symmetry that we imposed. G strong, the SU3 coupling constant, G, the SU2 coupling constant, and G prime, the U1 coupling constant. They will appear in the covariant derivatives of the various fields. And as I said, F and epsilon are the structure constants, known numbers. These are 3 parameters for all the gauge interactions, which have to be fixed by experiment. So these are known numbers, mathematical or group theory, and these are 3 parameters of the theory. So far, the theory has these 3 parameters. And all of them are real. Gauge couplings are always real. This is how the covariant derivatives look in general. There is as the space-time derivative, the part that belongs to the SU3 transformation that compensates for that. So it has this octet field and the corresponding generator of SU3. And we only need to know 2 things, because all the fields, scalar and fermion fields that I introduced, are in one of the 2, either singlets of SU3 or triplets of SU3. There was nothing else. So for singlets, it's simple, LA0. This way, e to the I, LA theta A is invariance. The generator annihilates the state, and so the transformation, the exponential of that, keeps it invariant. And for triplets, these SU3 generators are half of the Gelman matrices, 8 3x3 matrices. All the fields fermionic on scalar introduced are also just in two representations, either singlets or doublets. So also here we have just to know these two. For doublets, these are half of the Pauli matrices, 2 by 2 matrices. For singlets, the generator is 0. So this is how the covariant derivative acting on each of the 5 different representations is. So let me, since we've seen A left, E right, and phi, and since these 3 are singlets of SU3, then the covariant derivative is exactly for these 3 classes as appeared already in the leptonic standard model. They are singlets of SU3, so we will not get a term with the gluon, and the other ones are the same because they're in the same representations as S of SU2 cross U1 as they were in the leptonic standard model. So let us just look at these 3, the 3 quark fields. D mu of Q left I. Q left is the richest in quantum numbers. It's a triplet of SU3. So we have here this lambda A over 2 multiplying the gluon or the octet field. It was a doublet. It's 3, 2 plus a sixth. A doublet of SU2. So we have this term with the Pauli matrices and hypercharge plus 1/6. So it has also this. So the Q left, if you want, will couple to all 3 types of gauge fields. The octet of SU3, the triplet of SU2, and B. U right I was 3, 1 plus 2/3. 3, same term as here, because they transform in the same way under SU3 color. A singlet of SU2, so this type of terms will not appear here. And charge 2/3 hypercharge, that's the 2/3 here. D right I, also a triplet of SU3 and a singlet of SU2, so the same term here, and hypercharge minus a third. Again, all this comes from the assignment of representation to each of these, up to these 3 number, GS, G, and G prime, which need experiments to know what they are. So, we can already start constructing the Lagrangian. We have the kinetic terms for all the fields, the 3 multiplets of gauge bosons, the single scalar, and for each type of representation, summation over the 3 copies of the corresponding kinetic term, with the field strengths of each of these written explicitly on the previous page, with the covariant derivative acting on the field written explicitly in the previous page. So everything here is dictated and known. All fermion fields have hypercharge different from 0. And similarly, the scalar field. Sorry, but here it's because we are concerned with the fermion field. Since they have wide different from 0, we cannot write Majorana mass terms from them. It's charged under an imposed symmetry, no Majorana mass term. Moreover, sorry, all the left-handed fields are doublets of SU2. All the right-handed one are singlets of SU2. That also immediately tells us that the theory is completely chiral. There is not even one pair of left-handed and right-handed fermion that we can match and write for them a Dirac mass term. And so neither Majorana mass term nor Dirac mass term, the part that is purely fermionic beyond the kinetic term is 0. Other combinations that can couple to the scalar in the representation 1, 2 plus a half and will form a singlet, pairs of left and left or left and right, or sorry, left and left, right and right, or left bar right or right bar left. Yes, there are 3 such things, 3 such pairs in the representation. So all the following combinations, which are singlets of the Lorentz group. That's important because we want to couple them to the scalar. So L bar R, L bar R, R bar L, all of these. So this are Lorentz singlet or scalar. So this recombination, L bar E, as we saw already, Q left bar D right, U right bar Q left, all of them transform, or hence in them, a singlet of SU3 color, a doublet of SU2, hypercharged minus a half, which means that they can have Yukawa couplings with phi. So there are three 3x3 Yukawa matrices. One for the quarks with the U right, one for the quarks with the D right, and one, which we already saw in the leptonic standard model, for the leptons, plus the Hermitian conjugate of all of these. Phi tilde is phi dagger in its quantum numbers and exchange of the upper and lower component of phi for mathematical reasons, but the quantum numbers of this is 1, 2, minus a half. Q left bar U right is the opposite quantum numbers of U right bar Q left. So Q left bar U right is 1, 2, plus a half. And phi tilde, the opposite quantum numbers of phi, it's 1, 2, minus a half. So this is an allowed term. So 3x3 complex Yukawa matrices. Next step, what we've missed so far in here is the scalar potential. And by now you've seen it already 5 or 6 times. So here is the 7th. So we needed to lead to spontaneous symmetry breaking. The symmetry allows only these two terms in the scalar potential. And we choose mu squared smaller than 0 because in the definition of the model, we required spontaneous symmetry breaking. We have a single field, single scalar field. It must carry a vacuum expectation value to lead to spontaneous symmetry breaking. So mu squared is smaller than 0. It's convenient to define this V squared, where V or V over square 2 will be the vacuum expectation value. It allows us to write the same Lagrangian up to a constant term in this way, which makes clear that the absolute value of the vacuum expectation value should be V over square root of 2. And as before, we choose this to be in the lower component and the real part. So that's what's written here. And immediately we know, not immediately, just because we remember maybe what we said in the morning. As I said, it's a singlet of SU3 color. So all the SU3 color generators would annihilate this vacuum, and therefore SU3 is not spontaneously broken. And for the SU2 cross U1, we've already seen that it breaks it to the subgroup of U1 electromagnetism, and we prove that it's not any U1, but it really fits the properties of U1 electromagnetism, not by chance, okay? The model is constructed to do that, to have in the end the U1 electromagnetism, to have the massless photon, electromagnetic interactions. We want it to be part of the model, and we chose the quantum numbers so that it happens. So it's not by chance that this remaining U1 has the properties of electromagnetism. And okay, this is just what I said before. This tilde signifies conjugate, so the opposite quantum numbers, and there is exchange of upper and lower component. Since this is real, then automatically the vacuum expectation value of phi tilde has the V in the upper component, okay? Because this epsilon alpha beta exchanges the upper and lower. So that's it. We have the standard model Lagrangian. Kinetic terms for the SU3 octet, SU2 triplet, the U1Y gauge boson, the scalar, the left-handed quark doublets, the two types of right-handed quark singlets, differing by their hypercharge, plus 2/3 and minus 1/3, the lepton doublets, and the lepton singlets, doublets and singlets of SU2. So these are the kinetic terms. And again, all of these rich set of terms has in it only three free parameters, GS, G, and G prime. And they are hidden in the definitions of the field strengths and in the covariant derivative specific to each field. That's where they appear. We don't see them explicitly, but when we go back to what these are, we will see the G, G prime, and G strong. It has the Yukawa couplings, the three sets that we said before, for Q left bar U right, Q left bar D right, L left bar E right. Each of these is a 3x3 matrix of complex entries. That's why also the Hermitian conjugate here. And so a priori, a 3x3 matrix has 9 real and 9 complex parameters. So altogether, it's 27 real and 27 imaginary, it's 54. But the number of physical parameters coming out of that is much lower. So the number of parameters of the standard model will not turn to be that huge. And we have the scalar potential. That's the standard model Lagrangian. Instead of defining the model the way I did, which I like because it tells you what the symmetry is, it tells you what is the representation. One could start the investigation from the Lagrangian. The Lagrangian exhibits this SU3 color cos SU2 cos U1 local symmetry. But if we think that explaining things by symmetry principles is a nice way to understand nature, then it's better to start from the definition than from the Lagrangian that comes as a result out of that. So this is the Lagrangian, and now, this is not yet a spectrum, okay. One more slide, which repeats the thing that I did not say explicitly in the morning. There is a way to reach something called the unitary gauge, where the field phi has just this form, V plus H, where H is the real scalar degree of freedom, a single one. It's an expanding around the vacuum. H has vacuum expectation value 0. And the other three real scalar degrees of freedom that were here, the imaginary part here and the complex thing here, disappear from appearing explicitly. They are implicit in the vector, in some of the vector boson field, where there are now d mu of these 3 degrees of freedom, which will become their longitudinal component. So again, this is somewhat tricky and technical. This is a shortcut to that. So I'm just postulating it here. And now we can start to do what is the phenomenology of the standard model. So the first thing is to identify the elementary particles that it describes, and much of it is common with the leptonic standard model. And will save us work here in part, so let us see. Scalar, we said that we can use a specific gauge, the unitary gauge, where this is phi, so a single real scalar field. We already saw that it's electromagnetically neutral, that it has this mass. The scalar potential has the same form as the leptonic standard model, so this is still the expression for its mass. The only additional thing that we mention here is that it is, okay, I should say it. The exact symmetry of the model is now SU3 color cross U1 electromagnetism. So every elementary particles must have well-defined transformation properties under SU3 color cross U1. In the leptonic standard model, we only saw the U1 charge, the U1 electromagnetism. So now for each elementary particle, even if it appeared there, we have to say what is its SU3 color transformation property. And so this comes from the field phi that is a singlet of SU3 color. And this is the expression we use. Color singlets mean a singlet of SU3 color, which means that it doesn't couple to the gluon or to this octet field. Not surprisingly, the mass of the Higgs did not change from the leptonic standard model. Okay, it's experimental number. It's the same particle that we introduced there, and I'm still admiring the experimentalist for achieving the accuracy of 1 per mil. Vector bosons. Again, much of this we already saw in the leptonic standard model. We had this breaking, SU3 cross SU2 cross U1, with overall 12 generators, 8 for this, 3 for this, 1 for this, into SU3 cross U1, which has only 9 generators, 1 for the SU3 and 8 for the SU3 and 1 for U1 electromagnetism. So 3 generators are broken out of the 12. Automatically means that we will have in the model 3 massive vector bosons. So the new thing here are the degrees of freedom, the gauge bosons related to SU3. That's an octet. The symmetry remains exact, so it's massless, and the name that we give it is the gluon. So much of the things that have to do with SU3 we already encountered when we gave QCD as an example of a non-abelian local symmetry. We did that. There are here a little bit more subtleties, but this we already saw there. SU3 has the gluon, an octet of SU3, spin 1 and charge 0. Also, since we have an exact gauge symmetry, local symmetry, U1 electromagnetism, there is a field which is a singlet of SU3 cross U1, the photon field, and it's massless. And we already know that this does have self-interactions. This being part of a non-abelian, it necessarily has self-interactions, or if you want, it transforms under its own symmetry. That's the reason that it has self-interactions, while A, being a singlet of everything, does not have self-interactions at 3 level. So we have the gluon and the photon as 2 massless gauge bosons. So these are already 9, and we have to identify the other 3, and it's exactly the same identification as we did in the leptonic standard model. Those that are massive come from the kinetic terms of the scalar when we replace the scalar by just its vacuum expectation value, and this is what it gave for the gauge bosons related. The fact that A mu does not appear here is exactly this fact that it's massless, and the W plus minus are singlets of SU3 color. That's the new ingredient here. Charges plus minus 1. The mass is the same as we derived in the leptonic standard model. And the Z boson is also a singlet of SU3 color with this mass, and the rho equal 1 remains. The rho equal 1, so the standard model employs, and the leptonic standard model employ, for the sake of spontaneous symmetry breaking, a field that is a doublet of SU2. To break SU2 cross U1 into U1, what you need is, to U1 electromagnetism, what you need is a field that transforms under SU2 and has in it a component where T3 plus Y is 0. Because you want this to give the vacuum expectation value to this component, the component that will be annihilated by the T3 plus Y. But you could do it with other things than the doublet with hypercharge half. For example, you could do it with a triplet of SU2 that has hypercharge 1. It has 3 components of Q equals plus 1, 0, minus 1, or with a triplet of hypercharge, so 0, or with a triplet of hypercharge 1, and with higher representations. If you break the SU2 cross U1 with such multiplets, the rho equal 1 relation will be violated, sometimes very dramatically so. And so from the fact that this is consistent with experiment, we know that the dominant mechanism of breaking is by a doublet. Maybe nature has more higher multiplets of SU2 scalars, but their vacuum expectation value must be very small if they exist, because they can give deviations from this relation that are strongly constrained by experiment. But the model that we now employ, the standard model, has only a single doublet, and therefore this relation is its prediction. Fermions. So the key here is that all the fields were charged and chiral under SU3 cos SU2 cos U1, all the fermion fields. And therefore, they could not have masses if the symmetry were not spontaneously broken. And the question is whether under the unbroken SU3 cos U1, the fermionic fields that we have with these quantum numbers are either vector-like or neutral, in which case they can become massive. And the answer is yes for all. Yes, in the sense that they are either vector-like or complete singlets of SU3 cos U1, not necessarily on the question of whether they get masses. So let us see. So, to do that, we again do a similar exercise to what we did before. In the limit that SU2 cos U1 was unbroken, there was no sense in giving different names to the upper component and the lower component, because if the symmetry is unbroken, there is no way to distinguish between them in experiment. We can give them names, but let's say each quark is a triplet of SU3 color, okay? So we can invent names for these three. Many people call them red, blue, and green. That's why it's SU3 color, because they have colors. But there is no meaning to these words, okay? We never know whether the quark that participated in the process that we measured was red or blue or green. That's the meaning of a symmetry. But the SU2 is broken, and so we can distinguish in various ways between the components of the doublets. And so we give different names for the upper component. There are two types of doublets. There are the quark doublets. So we call the upper component up, and we call the down components down, or U and D. And similar, I change a little here notations. For the lepton doublets, I call the upper component N and the lower component E. It's a little bit change of notation. These are capital letters. So we now have these three U left, and they are triplets of SU3 color, and their electromagnetic charge is T3 equals plus half, Y equals a sixth, so their charge is plus 2/3. We have the U rights. They are singlets of SU2, so T3 is 0, and they carry hypercharge plus 2/3, so they also have Q 2/3. So we have these three and these three, which transform in the same way, a triplet of SU3 color and charge plus 2/3. Then we have the down component here. Its T3 is minus a half, hypercharge still is sixth, so electromagnetic charge minus a third. D right has T3 equals 0, it's a singlet of SU2, hypercharge minus a third, and therefore charge minus a third. So also these pairs of left and right-handed transform in the same way, triplets of SU3 color and electromagnetic charge minus a third. For the leptons, the lower component, T3 equals minus a half, hypercharge minus a half, electromagnetic charge minus 1. The right-handed here have T3 equals 0, hypercharge minus 1, and so charge minus 1. So we have pairs of E left and E right, which all transform as singlets of SU3 color, and electromagnetic charge minus 1, they transform in the same way. So we have here three pairs of these, 3 pairs of these, 3 pairs of these, that could get Dirac masses. We have a left-handed and right-handed that transform in the same way under the exact symmetry of the model, SU3 color, cos1 electromagnetism. And what is left are these upper component of the lepton doublets. There is no something corresponding right-handed, even though here I put what could have been, if we included it in the model, something that's n-right, which is complete singlet of SU3 cross SU2 cross U1, but it's not part of this model, but they are neutral. So, given that, and given these Yukawa couplings, indeed these Yukawa couplings give Dirac masses, or Dirac mass matrices, 3 by 3 matrices, to the triplets that are, the quarks that are charged plus 2/3, that's here, to the quarks that are charged minus 1/3, that's here, and to the leptons that are charged -1, that's here. So 3 by 3 mass matrices. For the charged leptons, we went through this, so just a quick look. We start with a 3 by 3 matrix. We insert unit matrices here and here in such a way that VE left, YE, VE right dagger is diagonal and real, which means we change basis and we give names to the charged leptons in this mass basis. The basis, if the Y is diagonal, we saw here that the masses are proportional to the Y matrices. So if we are in a basis where this is diagonal, then in that the fields in that basis are the mass eigenstates. So we call them E left, mu left, and tau left. Their partners, ni E left, ni mu left, ni tau left. And the right-handed ones, E right, mu right, and tau right. And we have these 3 charged lepton mass eigenstates. The electron, the muon, and the tau, they are all Dirac fermions. And also their partners in this model are mass eigenstates. They all have mass 0. There are no mass terms for these. They were not in the beginning and did not arise after spontaneous symmetry breaking from the Yukawa interactions. So that's with the leptons, 3 massive charged lepton, 3 massless neutrinos. And since the masses do not distinguish the 3 neutrinos, they have the same thing. The reasonable way to define them is by there being the SU2 partners in the doublet of the charged lepton mass eigenstates. And that's what their name suggests, ni E, ni mu, ni tau. Okay. So again, like in the leptonic standard model, they are massless in spite of their being neutral, which would have allowed in principle Majorana masses. And we saw that within the renormalizable leptonic but also standard model, there is a total lepton number carried by the neutrinos, and therefore their masses is not just 0 at the leading order, the 3 level, but to all orders in perturbation theory. And actually in the standard model, not in the leptonic standard model, this is a subtlety, not just to all orders in perturbation theory, but also non-perturbative. So this is a subtlety, why the leptonic standard model non-perturbative effects could give masses to neutrinos and here not. It's related to something called anomaly. So here there is an anomalous symmetry that forbids these neutrino masses, which means that that is S0 as one could ask for. Not even 10 to the minus 100 electron volt, okay? 0, real 0. So that's the prediction of the model for neutrinos. And they have said well-defined quantum numbers under SU3, cross U1, singlets, and neutral. Quarks. We go through a similar exercise. There will be a subtlety in this exercise, but not when we discuss the spectrum. It will arise when we discuss the interactions. So I'm now not telling you that there is a subtlety or what the subtlety is. We'll see it later. So we have this Yukawa 3 by 3. We do the same trick, put in a unit matrix, which is a V dagger V, where V is unitary, from the left, and another one from the right. Just change the place of the parentheses such that we transform YU by a B unitary transformation to real and diagonal form. We change basis. We call the real and diagonal form YU, YC, YT, with the convention that YT is the largest and YU is the smallest. And in the basis where this is diagonal, we give names to this upper component of the doublets. We call them U left, C left, T left. And the right-handed things that are relevant here, in this basis, there is a sense of giving them names, U right, C right, T right. The subtlety has that we here write also their partners in the SU2, DU left, DC left, and DT left. Okay, the subtlety is that these are not the quarks with charge minus third mass eigenstates. For the charged leptons, when we wrote down E left, mu left, tau left, and above ni e, ni mu, ni tau were mass eigenstates. So it was an interaction state. Things had well-defined transformation properties under SU2 cross U1, and also at the same time a mass basis for all the fermions involved. Here, again, all of these have a well-defined transformation properties under SU3 cross SU2 cross U1, but these down components are not mass eigenstates. With this notation, we have YU, this entry, times U left bar U right, YCV over square root of 2, C left bar C right, and this combination times T left bar T right. So we got three massive quarks, all of them triplets of SU3 and carrying electromagnetic charge plus 2/3. These are the up-type quarks mass eigenstates. So there are three mass eigenstates with well-defined transformation property under SU3 cross U1 electromagnetism, and they are Dirac fermions. It comes from Dirac masses, all of them, and they do not have Majorana masses. Same exercise for the down sector. So there was, what did I push? There was a general 3×3, a B-unitary transformation leads me to another basis where this Yukawa and therefore the mass matrix will be diagonal. So this is the mass basis for quarks with charge minus 1/3. The convention, I call this YD, YS, YB. This is the convention for the order of their sizes. In this basis, I give names to the lower components, D left, S left, and B left, and to the right hand and down, D right, S right, B right. And the upper component are their SU2 partners. These are not the mass eigenstates of the previous slide. These are not U, C, and T. These are mixtures of U, C, and T. Same as here, the down components are not D, S, and B. They are linear combinations of D, S, and B. And we get three Dirac fermions, mass eigenstates, where the masses are proportional to the corresponding Yukawa coupling and well-defined transformation properties. So, all charged fermions, we've seen now, acquire Dirac masses as a result of the spontaneous symmetry breaking. They were chiral and charged under the full imposed symmetry, but under the symmetry that is not spontaneously broken, they are vector-like, all the charged ones. The E, mu, and tau, 1 minus 1, left and right. The U, C, and T, 3 plus 2/3. The D, S, and B, 3 minus 1/3. Well-defined quantum numbers, and the same for the left-handed and right-handed. So vector-like representation of SU3 color cross U1 electromagnetism. The left-handed neutrino fields, ni E, ni mu, ni tau, are neutral under SU3 color with hypercharge, and they do not acquire masses due to the details of the particle content. They could, in a more general model, because they are neutral, they could get Majorana masses, but not in the renormalizable Lagrangian of the standard model. Okay, so let us skip this. Yeah, okay, let us not skip this. As I said, this basis, where the Yukawas for the charged leptons are diagonal, YE, mu, Y tau, in this basis, it's simultaneously an interaction basis and a mass basis. So the SU2 partners, Ni, Ni, mu, Ni, tau, are also mass eigenstates. So it's simultaneously interaction basis, where all fields have well-defined transformation properties under SU3 cross SU2 cross U1, and a mass basis, where all fields have well-defined masses and well-defined SU3 color cross U1 electromagnetism quantum numbers. And said it's a result of the degeneracy of neutrinos. So no matter which set of three neutrino eigenstates you choose, since they are degenerate, it will always be a mass basis for the neutrinos. For quarks, this is not the case. So to transit from the basis of an arbitrary basis for which we started to the mass basis of the up quarks, there was this transformation of the left-handed quark triplet, something with a matrix VU left. To get from that original basis to the basis where the down quarks are the mass eigenstate, there is a different transformation of the Q left. So we go to a different basis. And if VU left were equal to VD left, then the down mass eigenstates and the up mass eigenstate would be SU2 partners of each other. The left-hand ones would be in doublets. But if VU left is different from VD left, these are different bases. And so the mass basis for the up is different from the mass basis for the down. There is a combination, so perhaps I should say this. What is VU left and what is VD left depends on the basis from which we started. And there are infinite number of bases from which we could have started. And so these cannot be physical quantities. But whatever basis we started for, this combination, VU left, VD left dagger, is the same. It doesn't matter from which basis we started. It's a short proof, but I will not do it now, which tells us that maybe this combination has physical significance. If it's basis independent, it's something invariant, then there is a chance that it is physically observable. Now it has some interesting feature. For example, in the up mass basis, the down Yukawa is this matrix V times the down diagonal matrix. In the down mass basis, the up mass matrix is V dagger times the diagonal up Yukawa. So it plays this role. So again, VU left, VD left, each depend on the basis from which we start, but the combination does not. So there is a chance that it's physical, and this chance is indeed there. It is a physical matrix. We can measure its entries. It's called the Kabibo, Kobayashi, Maskawa, CK matrix. This is Kabibo, this is Kobayashi, this is Maskawa. In 2008, Kobayashi and Maskawa got the Nobel Prize because, in addition to suggesting these things, a few things that we'll come back to on this matrix, they realized that it includes CP violation, which could explain the CP violation that was observed in the experiment. Very much to the unhappiness of the Italian community, Kabibo did not get the Nobel Prize, which is controversial, but that's the case. He was the first to understand some of these subtleties in the two-generation framework, where indeed this matrix does not lead to CP violation. Say that I was very fortunate to be invited to the Nobel festivities in 2008 when these two got the Nobel Prize. I could spend a whole hour telling you things about the week that I spent there. But some of the things that I would like to tell you in this context, I should not be recorded. So since I am recorded, I will not. Perhaps over tea here and there. It was a wonderful week in my life, I have to say. So the most positive thing is that it's a whole week of ceremonies and festivities. The highlight is the Nobel ceremony and the dinner that comes after that in the town hall of Stockholm. But the thing that struck me is that it's a whole nation, the Swedish nation, for a week celebrating intellectual achievements of humanity. And it's a big week in Sweden, okay? The dinner that comes after the Nobel ceremony goes on for 4 hours and has all kinds of features in it. And this dinner is broadcasted live in the Swedish television. And as far as I know, and at least then, it is the most watched TV thing in Sweden. It's dinner, okay? We eat. That's what we do. Okay, there are shows by students and things like that, and there is dancing in the end, but the 4 hours event broadcasted live. So the Swedish really celebrate intellectual achievements. How many events are so encompassing and related to science, to literature? So I think it was a very nice feeling on that side. The personalities involved are very interested, Kobayashi and Masukawa, but that's for tea time and not for now. Also, as I mentioned yesterday to Sabila and Poonam, the way that I was forced to dress there is a dress code in the Nobel ceremony, is also very interesting, and pictures of me there will make you laugh. So I will not show you pictures of myself there. For short, Kabibo Kobayashi Masukawa is called the CKM matrix, and it's an issue of much investigation, but we'll see where it comes into the game. So far, it's just kind of a mathematical entity that we understand is basis independent, and it's made of two quantities, each of which is basis dependent. So the separate matrices, VD left and VU left, the matrices that diagonalize from the left, the mass matrices for the up and down, each of these separately cannot be physical. This product can and is physical. So we finished with exploring the spectrum. This is the standard model spectrum. So the new lines here compared to the leptonic standard model is the gluon field, spin 1, octet. Well, the whole column here is new because that's an additional symmetry, exact symmetry. So everything, almost everything is a singlet. The gluon is an octet, its electromagnetic charge is 0, and it's massless because it's an exact gate symmetry. The scalar content is again the single real scalar field that is spin 0, singlet of HU3 color, charge 0. There are the 3 charged leptons that are singlets of HU3 color, the 3 neutrino that are also singlets, and all other properties the same as in the leptonic standard model. And we added the quarks, up, charm, and top, spin half, triplets of HU3 color, charge plus 2/3, masses, here it's all in units of V, proportional to their Yukawas. D, S, and B, down, strange, and bottom, spin half, triplets of HU3 color, charge minus 1/3, and their masses proportional to their corresponding Yukawa couplings. And I think it's 4:30, so I should stop here. Tomorrow we start with the interactions, and then we'll also discover where the CK matrix plays a role. So that's it.
Which one? Here. So the question is from Debabrata Sahu. Is there any systematic way to check if in a theory there is any accidental symmetry or not?
If there is an accidental
Symmetry or not?
I think it's a good question. So I don't know of a systematic way to see from the definition of the model or to see from the spectrum, etc., whether there is an accidental symmetry, and if so, what it is. Accidental symmetries are identified in the mass basis. So I think it's very difficult to guess whether there would be and what would be accidental symmetries if you have the Lagrangian in the original manifestly symmetric under the full group Lagrangian. When you identify the mass eigenstates and you can write the Lagrangian for the mass eigenstates, this is where you see it. But but I think there is, so if one of you knows a way to say this model, you look at the definition or you look at the original Lagrangian and say, in the end, this model must have an accidental U1 to the 4 symmetry, which is what we will discover about the standard model. I will be delighted to learn that. I know it either from looking at the interactions with the various mass eigenstates, or because someone has told me that it's there and I checked and it's there. I don't know of a systematic way. It doesn't mean that there is no systematic way. I'm not aware of what it is.
There's one more question from Shubhajit Kala. We know that there is no right-handed neutrino in the standard model, but what about the Majorana type neutrinos? How to calculate degrees of freedom of Majorana type neutrinos?
So we know there is no right-hand neutrinos, but how about Majorana neutrinos? And then I didn't get the end of that sentence.
How to calculate the degrees of freedom of Majorana type neutrinos?
So it has two components, unlike Dirac fermion, which has 4 components, and that's it. So a Majorana particle has 2 degrees of freedom.
Yeah. So local, offline participants, any questions?
So if it is if it is this neutrino is a fermion, if neutrino is a fermion, so it should satisfy this Dirac equation. So gamma mu p mu minus m psi. So psi is 4 component. So I suppose when we are saying that there's a left-handed neutrino and right-handed neutrino is not there, we are perhaps assuming that one component is actually in the
we could either
energy range and the other one component
1 minus gamma 5 or 1 plus gamma 5. Dirac was interested, I think, in 1928. He did not know that there are neutrinos at all, right? It came later, the suggestion by Pauli, that there are neutrinos, and experimental verification came even later. As long as you deal with charge fermions, and he was interested also in the charge fermions and the electromagnetic interactions, charge fermions are necessarily Dirac fermions. Mm-hmm. So I think he was not necessarily interested in that. And I think later, I don't know the exact chronology, Majorana came with the suggestion of this possibility of 2-component fermions and the equation for them. So Dirac, I think, I don't know if he missed the possibility to separate it into 2 Weil fermions, the Dirac fermions, or whether he was just not interested because any charged fermion is Dirac fermion, and it's these 4 components. And you know the stories about Majorana that was on a ship and then disappeared, and some people think he probably the more likely possibility is that he committed suicide for reasons that we don't know. But there are also legends, like some other celebrities from time, that he didn't really die, but disappeared somewhere and hid himself from society, like James Dean and Elvis Presley and some others. It's nice legends, but anyway, it's a kind of tragic figure with beautiful achievements, and the fact that in the end, it's not yet experimentally proven, but I strongly believe that neutrinos are Majorana particles, and we'll talk about why we don't know yet experimentally whether they are Majorana or Dirac. But I think it's beautiful that in the end, nature probably realized this possibility of having Majorana fermions and not just Dirac fermions. It's nice in some way.
So, okay, maybe we should thank you, see again. And
He has a question.
I have a question.
Yeah. So don't thank me again yet.
So when we say coupling constant means the strength of interaction.
Okay. So usually, when we say coupling constant, in particular when we refer to this GS, G and G prime that appear in the covariant derivatives. So first of all, we mean this parameter in the Lagrangian, okay? The covariant derivative is in the Lagrangian, and we mean a parameter in the Lagrangian. We later see, when we discuss the interaction, that all the strong interaction, let's say, related to SU3 color or to the gluon field, all of them, the self-interactions, the interaction with fermions, depend on this one parameter. So the overall strength is this G strong, but the exact thing could depend on which representation under SU3 color the gluon is interacting with. Perhaps it's clear for the photon. E is the overall strength of the photon interactions. So all photon interactions are proportional to E, but each one depends also on the charge of the fermion to which it couples. So the strength of the coupling, any particular one, is EQ. So, but all of them are proportional to E, okay? So it's the overall measure, and when we say E is smaller than G, is smaller than G strong, yes, it tells us about the overall strength of this, but there is, for a specific process, there is also the question of which charge or which SU3 representation interacts with. So these coupling constants are not the entire answer, but they are common to each kind of interactions.
So when we say structure constants, what is the meaning of structure constants? Like F, A, B, C, in one of slide you have defined the structure constants also.
So this define what we call the algebra of a group. So it's a mathematical thing, it's not a physical parameter. So let's say SU3, the commutation relation of two generators of SU3, TA, TB, is I, F, A, B, C, TC. And A and B and C runs from 1 to 8. So if you want F, A, B, C, each of its three indices runs from 1 to 8. And for each combination, there is a number. It's a mathematical number. It's part of the definition, the mathematical definition of the group.
It's just a mathematical number, structure constant, or does it have a
it
physical?
appears, it does appear, okay. It does appear in the gluon self-interactions. So when we look, I didn't discuss it at all because There is not phenomenology of the gluon self-coupling. It's difficult to measure, but the gluon, yeah. So the FABC tell you whether a red and a red gluon will collide, what would happen, or a red and a blue. ABC, sorry, this is not the gluon, the quarks. So the FABCs do tell you within SU3 which combinations are allowed or not. But since we cannot say whether a gluon is this type or this type of the 8 possible states, then in the end it's a sum over all of them that's in some sense. So they play a role when you look at specific thing, but these are like numbers that are known and appear in the calculations. So they do appear in the calculations, they do affect them. But it's not something to be fixed by experiment. It's something which is mathematical. It's part of the group properties. And so it's dictated by features of the group. So we know what it is for each of them.
Thank you. Ma'am.
Okay.